Hello, and welcome to today's lesson, which looks at uncertainties in the measurements and errors topic for AQA A-Level Physics. Now, in today's lesson, what we are going to do is we're going to try and understand and calculate uncertainty. Now, if we're successful and we learn in today's lesson, we understand the importance of uncertainties, we can determine the absolute and percentage uncertainty in values, and finally we can calculate combined uncertainties in values, which links into the following part of the AQA A-Level Physics specification 3.1.2 Limitation of Physical Measurements. Now, in science, there's always some error in your measurements. Now, this is because there's at least some uncertainty in the measuring devices used to measure variables. There's an uncertainty in things such as your stopwatch, which is governed by set rules, and in addition, there's more uncertainty placed on a reading due to experimental error by the experimenter. For example, the reaction time. Now, this is determined by your own judgment. Now, the uncertainty value placed on the measurement reading is a combination of both factors, and we can call this idea the error of the value. So overall error is the uncertainty in the measuring device, which is set by rules, plus the uncertainty in your experimental technique, estimated by your own judgment. Now, in your results, you should always write down a numerical value of error with your experimental value. This error gives you a range of values that the measurement must lie in. So, for example, if we say an answer is 2.5 volts plus or minus 1 volt, this tells you the value could lie between 2.4 volts and 2.6 volts. So it also indicates the confidence you have in the values that you have. Now, what that means is that if, for example, you say the potential difference is 10 volts plus or minus 2 volts, this tells us you are very, very confident that the result lies between 8 volts, 10 minus 2, and 12 volts, 10 plus 2. Now, a large uncertainty indicates that you are sure the result lies within a wide possible range, which gives you a low confidence in a particular value because you're spreading out the values with which you think it would lie within. However, if you have a small uncertainty, this indicates the result lies within a small range of values, which gives you high confidence in a particular value. So, for example, we think if it's 10 volts plus or minus 2 volts, it will lie between 8 volts and 12 volts. Now, the measured value might be 10 volts, but it could be as low as 8 volts or as high as 12 volts. The actual value lies within the range. Now, all experimental values should be presented in this format with an uncertainty. Now, the range of possible values takes into account the mistakes you make with your experimental technique and the resolution of the measuring device used. Now, you can have things called absolute uncertainty. Now, that is a numerical value, which is the combination of measuring error and experimenter error. But you can also have percentage uncertainty, which is a measurement of the percentage of the uncertainty compared to the value that you are using. Now, in scientific A-level investigations, you can write your experimental value with either uncertainty, either the absolute, which is a numerical value such as plus or minus 0.2%, or the percentage uncertainty, which is a percentage of the measured value that you've taken. Now, you never ever write a value without an uncertainty if you take a measurement. So you can't just write 7 amps as an answer anymore. Now, generally, you can write your uncertainty as either the absolute or the percentage. However, there are some situations where one is better than the other, and I'll discuss that later on in this lesson. Now, previously, when taking measurements in results table, you might have illustrated your results table as such, with your quantity measured with the unit of quantity there. Nowadays, you've got to include the uncertainty in there underneath the unit measurement. So, for example, the current through the wire in amps plus or minus 0.05 amps, which tells us A, the value you're measuring, B, the unit that it's measured in, and C, the uncertainty in that particular measurement. But what do we mean by uncertainty and how can we determine it? So, as we mentioned before, every measurement has an inherent uncertainty, and the important question to ask is whether an experimenter can be confident the true value lies in the range that's predicted by the uncertainty that is quoted. So, uncertainty is a quantitative measure of how much your measured values deviate from each other. Now, there are many different methods of calculating uncertainty, each of which is appropriate to a different situation. Now, if the measurements are not very precise, they vary in their repeats, then the uncertainty of the value is very high. Now, good experimental design will attempt to reduce the uncertainty in the outcome of any experiment. The experimenter will design experiments and procedures that will produce the least uncertainty uncertainty and provide a realistic outcome, okay, and a realistic uncertainty for those values. Now, in assessing uncertainty, there are a number of values you've got to consider. The resolution of the instrument, the manufacturer's tolerance when they've made the instrument, the judgments that are made by the experimenter in the investigation, the procedure that the investigator adopted, and finally the size of increments available. Now, a combination of all these above factors means that there's no hard and fast rules about the actual uncertainty in a measurement. It is down to estimation in certain instances. So you've got the calculation ultimately is down to the discretion of the experimenter at the end of the day. Now, there are 4 ways to calculate the absolute uncertainty in a value, which is the numerical value of uncertainty. Method 1 is calculating the uncertainty due to the measuring device used. Method 2 is calculating the uncertainty due to experimental technique. Method 3 is calculating the uncertainty due to a given value that's been stated. And method 4 is calculating the uncertainty due to a variation in repeated readings. Now, we can assess from an instrument's resolution the minimum possible uncertainty, which is method 1, but only the experimenter can assess the other factors, method 2, method 3, method 4, based on the arrangement and the use of the apparatus, and a very rigorous experimenter would draw attention to these factors and take them into account in their overall analysis. Now, once the absolute uncertainty has been calculated, we can then work out the percentage uncertainty. Now, when questions use the term uncertainty, they refer to absolute uncertainty, not percentage uncertainty. You only calculate percentage uncertainty when a question explicitly states the phrase percentage uncertainty. Now, an absolute uncertainty can only be reduced by improving your experimental technique or by carrying out more results. So, we're now going to review the first method for calculating absolute uncertainty. Now, you know that there are 2 types of readings that can be measurements that can be taken in a physics experiment. The first type is a reading. Now, these are values found from a single judgment when using a piece of equipment. So this ultimately means looking at a device once to take a measurement. So what this means is, for example, let's say we've got a balance. You only take one judgment when you use a balance because you only look at the balance once. So this therefore makes it a reading. So one judgment equals one reading. Now, if you have to look at the device twice, you've got to take a judgment of 2 values. It then becomes a measurement. So looking at a device 2 times is a measurement. Now, when measuring the length of a wire with a ruler, you look at the wire twice. So therefore, this is a measurement. So 2 judgments of the measurement of the device, it equals a measurement. So as a general rule, you can split measuring devices into things that produce readings, which is 1 judgment only, and measurements, which require 2 judgments. Now, the uncertainty in a reading is going to be plus or minus the half of the smallest division of the measuring device. So for example, if the resolution of a thermometer was 1 degree Celsius, then it's going to have an absolute uncertainty of plus or minus 0.5 degrees, half of the resolution, 1. That's because you're taking 1 value from this device. So say for example, you're reading this value as 30 in this particular picture. Well, if you look at this particular scale, it could be between 29.5 and 30.5 because you're not sure what that value is because they're not actually marked on the scale. So therefore, there's now an uncertainty due to the scale of the measuring device. So therefore, it is 30 plus or minus 0.5 because when you add 0.5, it's 30.5. When you minus 0.5, it's 29.5. So it's very, very important that you do this. Now, it's also important to note that the uncertainty in the value are given to the same number of decimal places. So it will be 30.0 plus or minus 0.5 degrees Celsius. Now, if you're taking a measurement, you now need to take 2 judgments. So you've got to think of 2 uncertainties. So because both judgments have a plus or minus half of the scale division, as stated previously, they combine. So a measurement has an uncertainty of plus or minus the smallest scale division because it's the twice because you're looking at it twice. So therefore, that uncertainty has been doubled. So therefore, on a thermometer with a resolution of 1 degree Celsius, that tells us that the plus or minus uncertainty is also going to be 1 degree Celsius because the plus or minus 0.5 from each judgment is going to be added up. So for example, when you use a ruler to measure length, because you're looking at the start of the object and the end of the object, it is a measurement because you're looking at the device twice. So therefore, the measurement of a ruler could lead to an uncertainty of plus or minus 1 millimeter. So to summarise, the uncertainty of a reading, which is when you make one judgment from a measuring device, is half of the smallest scale reading. But the uncertainty of a measurement, which is 2 judgments, is plus or minus 1 of the smallest scale reading. So the second method to calculate uncertainty is due to experimental technique. Now, this is basically where an experimenter has to estimate an additional uncertainty due to poor experimental technique. So for example, a stopwatch might have a resolution of plus or minus 0.01 seconds, so in the previous methodology that gives us an absolute uncertainty of plus or minus 0.01 seconds because you look at a stopwatch twice, once to start it, once to stop it. However, you would know that there's going to be a bigger absolute uncertainty than plus or minus 0.01 seconds because there's the reaction time of the experimenter to consider. So at this point you've got to add that absolute uncertainty to your measuring device to give a larger uncertainty value. So if you think the experiment is causing more uncertainty by carrying out the measurements than the device produces from its resolution, you've got to state this uncertainty and not the measuring device uncertainty. So an example would be if a student measures the length of a piece of wire, it's very difficult to hold the wire completely straight against the ruler. So the uncertainty of their measurement is likely to be higher than the plus or minus 1 millimeter uncertainty of the ruler. So depending on the number of kinks in the wire, the uncertainty could be thought of as either plus or minus 2 or 3 millimeters. Now to clarify, this is an estimation made by the experimenter. So as a result, there's no right answer for this particular uncertainty. It's just got to be an appropriate estimation. Another example could be that a digital voltmeter or ammeter will fluctuate due to the connections in there, which will mean that it will have a greater uncertainty than the resolution, which you've just got to estimate. And again, we talked previously about the reaction time of a human being using a stopwatch is going to produce an absolute uncertainty greater than the uncertainty predicted by its resolution. So the next particular method is looking at the uncertainty due to a stated value. Now, if you have a stated value, such as a constant, then what you have to do is you assume the uncertainty to be plus or minus 1 in the last significant digit. Now, the uncertainty may be lower than this, but without knowing the details of the experiment to produce that value and the procedure that led to the value, there's no evidence to suggest otherwise. Now, an example of this will be the following. If you quote your value to be 3.5 times 10 to the 3 and you're told that's a stated value, well, therefore you look to the last significant figure, which is 0.1, and therefore you say the uncertainty is plus or minus 0.1 times 10 to the 3, and therefore that will give you your absolute uncertainty. Now, method 4 is calculating the uncertainty due to variation in repeated readings. Now, if you have repeated values and then derived a mean, the absolute uncertainty can be calculated from the variation in the repeated readings. This comes from the idea that the maximum possible value for the result is the largest value of the repeats, and the minimum possible value for the result is the smallest value of the repeat readings. Now, when you do this particular practice, you must remove the anomalous results first. So what you would do to work out your absolute uncertainty is find your highest value, find your lowest value, then minus 1 from the other to find your range, then do range divided by 2, and that will give you your absolute uncertainty. Now, this happens because you're confident that the value lies within the highest value recorded and the lowest value recorded. So in an investigation where repeats are taken, the experimenter has to be confident that the true value lies within the highest part of the variation and the lowest part of the variation. So we can assume that the answer is the middle point between the highest and lowest value, and so you're confident the answer lies in that range and allows you to represent this with a plus or minus symbol. So it's going to be half of the range recorded. So for example, in this one, the biggest value is 2.00 meters, the lowest is 1.80 meters, so therefore the range is 0.20 meters, 2 0.00 minus 1.80, and therefore you half it because our uncertainty is plus half and a minus half to get the full value, so therefore it's plus or minus 0.10 meters. Now we can calculate the percentage uncertainty from the absolute uncertainty by carrying out the following equation. Percentage uncertainty is equal to the absolute uncertainty divided by the value times by 100. Now if you're using a mean value, it is then absolute uncertainty divided by the mean times by 100. Now the absolute uncertainty for repeated measurements can be worked out from our previous methodologies, and it's good practice to reduce percentage uncertainty to the lowest value possible, and the easiest way to do that is to use the largest values in your experiment, because when you divide by a larger number in this particular equation, it will give a smaller percentage uncertainty. So you could also do this by decreasing the absolute uncertainty, and that could be done by carrying a better experimental technique or using measuring devices with smaller resolutions. Now an example calculation of percentage uncertainty is as follows. So let's say it's 10 amps plus or minus 0.1 amps. So to work out your percentage uncertainty, you do 0.1 the absolute uncertainty divided by the value 10 times by 100, and it's 1.0%. Now note, you don't have to write a unit down for percentage uncertainty because it's a percentage, and it's got to be written though to the same number of significant figures as the value that has been given in the question. Now, when dealing with complex formulae and equations in physics, we will have uncertainties from different values. So say, for example, you have power. Well, power equals potential difference times by current. So you might have a uncertainty in the potential difference measurement, you might have an uncertainty in the current measurement. So to work out the uncertainty in the power measurement, it's got to be a combination of those two other uncertainties. Now there are rules to combine uncertainties to work out values. So the first rule is if the equation includes a plus or a minus, an addition or a subtraction, you have to add the absolute uncertainties. So say for example its extension equals stretched length minus original length, and let's say the stretched length had an absolute uncertainty of plus or minus 2 and the original length had an absolute uncertainty of plus or minus 1. Well, you add the two values regardless if it's an addition or a subtraction, and therefore you get plus or minus 3 as your absolute uncertainty. Now, if you're multiplying or you are dividing, such as in resistance equals potential difference over current or power equals potential difference times current, you now add the percentage uncertainties. Now, it doesn't matter if it's a division or a multiplication because you're considering both terms to work out your value in that particular equation, so you've got to always add the percentage uncertainties. So let's say the percentage uncertainty in potential difference was 4%, the percentage uncertainty in current was 3%, so if resistance equals PD over current, it's therefore going to be 4% plus 3% equals 7%. Now, if you have a power in your equation, so for example, area equals pi r squared, well, what you've got to do is if you have a power value, you've got to multiply the percentage uncertainty by the power. So let's say, for example, we were working out volume, and volume equals length cubed, and you know your percentage uncertainty of length is 2%, so therefore you do 2% multiplied by the power value, which is 3, so it's 2 times by 3, which is plus or minus 6%. So to summarize our ideas of uncertainty, we need to know the following. Uncertainty is a measure of how certain you are of a value. It's the range of values you are sure the result lies in. Now, the absolute uncertainty is an uncertainty expressed in a value, where it could be absolute uncertainty equal to value times by a percentage uncertainty over 100, whilst the percentage uncertainty is the uncertainty expressed as a percentage of the value, so it's absolute uncertainty over value times by 100, and when we mention uncertainty we are referring to absolute uncertainty. There are four ways to calculate absolute uncertainty. You can calculate it by looking at the measuring device, and it's the resolution of the device if it's a measurement, and it's half the resolution of the device if it is a reading. Now, if you are calculating uncertainty due to experimental technique, that is an estimation. If you're calculating uncertainty due to a stated value, it's plus or minus 1 of the last significant figure in the value, and you can calculate uncertainty due to the variations in readings, and that is the range of repeated values divided by 2. Now, we can combine uncertainties if you have more than one uncertainty in your equation. If you are adding or subtracting values in an equation, you add absolute uncertainties. If you're multiplying or dividing values in equations, you add percentage uncertainties. And if you're using values with powers, you multiply the percentage uncertainty by the power. So, in this lesson, we should be able to evaluate results and draw conclusions with a reference to measurement errors and uncertainties. And with uncertainties, you can do absolute, fractional, and percentage uncertainties, which will represent uncertainty in the final answer for a quantity, and you can combine absolute and percentage uncertainties. So if you've been successful and you've learned in today's lesson, you understand the importance of uncertainties, you can determine the absolute and the percentage uncertainty in values, and you can calculate combined uncertainties in values. I hope you've enjoyed today's lesson looking at uncertainties in measurements and errors, and have a lovely day.